Let's figure out the temperature at the bottoms. How do we figure the temperature of the bottoms? We need to build a best estimate of the composition of the bottoms. And in this case, assuming that they have a really good distillation column, so the bottoms are going to have all the vinyl chloride and dichloroethane. Sorry, vinyl chloride and dichloroethane. We can look at the product, and we see that we have, oh, I didn't put the dichloroethane. Let me put the dichloroethane here. So I'm going to open it. Sorry, I thought I had it on. The laptop I have it on. It should be projecting. Weird. I'll turn it off and back on. It's connected.
Is there any setting right now?
But now it's blinking off. Okay, now it's off. Looks like we may have it on my drawer. Well, you can check it yourself. If you go to your simulation and put the D string, click on the D string. Okay, I'm not projecting it, but everybody click on the D string. Go to composition and select, instead of mole fractions, select on the basis molar flows. What? Yes, the projector is off. That's problem. Go to your Unix file where we just had the vinyl chloride simulation. Go place to your D stream. That's the stream that has vinyl chloride, HCl, and dichloroethane. And look at the molar flows of not the HCl, the other two components. Actually, let's look at the molar or mass. Either. You can look at either molar or mass flows. Let's look at mole flows. And you will see that, let me write it. Since we, if I can get that projecting, okay, it's off now. This is maybe not. But if it comes back on, we'll check it in. At the moment, it's not coming back on. So if you look at the simulation that we run, you find out that the composition coming out of, we have the D and we have the B, and you find that decomposition, and I write it in molar flows, gives us molar flow of vinyl chloride 1622.8, oh, it came back. Okay, let's see. Laptop. Let's see if it goes to my laptop. Let's switch to my. Okay, switch to my laptop. Okay. All right. So you'll see that the molar flows. Okay, so I clicked on the district. Okay, click on the district. And go to components, to composition, and select on basis molar flows. And you see that the vinyl chloride molar flow is 1622.8, and the dichloro, oh sorry, wrong stream. Sorry for that.
The B stream?
The V stream. Go to the V stream. V stream, composition, and take molar flows. Okay, I have mass flows. That would work also. Okay, leave it. Okay, leave it. So you can see vinyl chloride is 1622.8 and dichloride is 953.07. Okay? So 1622.8 and 953.07. So we have this mixture. We're ignoring the two small components. Okay, we're ignoring ethylene and chlorine. So we consider only the three main components. And the distillate will have our HCl. The bottoms will have those two components. Okay? And how do we find the, actually, you know something? Since we have all the components here, we could even easily do it with all the components. Except, no, no, because the other would not come at the bottom. Okay. Because that's what feeds the distillation column. And the HCl, the D stream was already separated this out. And essentially, the reaction, what we're doing now, the distillation column, is this thing here we designed. So what leaves, bottoms, no, that was not correct. This is basically the combination of the two distillation columns. But what leaves bottoms is not leaving as bottoms in the first column. Because you're following the path and we first remove HCl, and then we're going to separate vinyl chloride and dichloride. So after we remove the HCl, we will have 122.8 vinyl chloride and 953.07 chlorine. So how do I find the temperature of this thing?
Should be the boiling point of the heaviest.
Say boiling point. If I have few components, yes, I have a boiling point. If you have a mixture, not boiling range, what comes into play instead of boiling point in distillation columns or any vapor-liquid equilibrium? We separate the vapor from a liquid, and it's in equilibrium. What would be the temperature if I have saturated liquid at a given pressure? What would be the temperature? What is the name for the temperature? Say it? Bubble point. And if saturated vapor, dew point. So the bottoms is going to be at the bubble point of the mixture. So we're going to create a stream that has these two components at these molar flows. And what will I do to find that temperature? I will set vapor fraction now 0. Now it makes a difference. I forgot to show you before, when I have the pure, I did first pure HCl. Pure HCl, we put 0, we got minus 14.7. Let's change to be 0.5, minus 14.7. Let's change it to 1, minus 14.7. For pure component, of course, boiling point coincides with bubble point and dew point. But if we have a mixture, that's no longer the case. And the saturated liquid is bubble point, and the saturated vapor is dew point. So I will create that stream. So let's quickly make it. So here is, let's put it over here. So I'll first define the composition, and I'll define it as molar flows, since that's what I wrote here. So I have molar flow of vinyl chloride, X. That was 122, no, 1620. 1622.8. And the dichloroethane was 933, 953.07.
It's HCl.
Oops. And thank you. 953.07. So that's the composition. Click OK for the composition. Go now to everybody okay? All right. So these are the compositions of what comes out in the bottom stream. And what comes out of the reboiler is always going to be at the bubble point of what happened. What comes out of a condenser depends on what type of condenser you have. If you have a total condenser where you make everything liquid but don't supercool, then the condenser will have distillate at the bubble point. But often you use partial condensers where you only condense the reflux and you let the distillate live as vapor. Then the distillate will be where? At the dew point. And that's one way to reduce cooling costs. In design, there are always a lot of trade-offs. And the trade-offs of cost. So obviously, if you use a partial condenser instead of a total condenser, always dew point is higher temperature than bubble point, okay? That means cheaper refrigeration. But on the other hand, you have now a distillate that is vapor. And if you have to transport vapor, transporting vapor is a lot more expensive than transporting liquid. And if you have to pressurize vapor, it's more expensive than pumping up a liquid. So a lot of things boil down to trade-off, and you need to do some economic analysis to find out what is better. Anyway, so these are the two components we have here, and to find the temperature of the boiler, we go to conditions. We're going to put the pressure, which is 12 atmospheres, neglecting the small pressure change we'll have in the column. And in this case, it makes a big difference what vapor fraction is. You have to put 0. This is the bubble point. So you can see that the bubble point temperature living is 197 Fahrenheit, or if you hover over it, 92 degrees C. Okay? So the reboiler will be living at 92 degrees C. Your text has 93 degrees, 1 degree difference. Okay, what I'm doing is unison what your text has, simply giving you the results. I'm showing you how you actually get what your text has. All right? So 92 degrees would be the temperature of the reboiler.
So you don't really have to consider the other two the other stuff that's
it would, okay. In reality, the other two are more volatile, vinyl chloride. If you need to get rid of them, you would put a distillation column first to get rid of those two.
Okay.
So here I would have, here Tim's question, if I was considering the other two, then I have 5 components, and the order of the 5 components would have been, well, I'm not sure, okay, HCl, I'm pretty sure chlorine is lighter than HCl. Well, or we could have, okay, if we had the other components, chlorine and also ethylene are lighter. I'm not sure of the order of those 3, but we could again have the first column, and I wouldn't be getting HCl, pure HCl out. I would be getting the mixture of the 3. Okay? I could actually figure it out on this simulation, because if I click on V, what really would be living at the top would be the mixture of 203 ethylene, 174 chlorine, and 1622 HCl. So instead of minus 26 degrees, we would have a different temperature there. We could do exactly what we did here, and we can actually, let's do it. Suppose that we had the other 2 components. Let's consider the other 2 components. Then I will do the split here between those 3 and vinyl chloride. Okay? Like we did here. So here wouldn't be just HCl, here would be HCl, chlorine, and ethylene. What would be the temperature of those three at 12 atmospheres? It depends what type of condenser I choose. If I choose a total condenser, it will be colder than if I choose a partial condenser. And we can see what the temperature will be in a second. So let me create a string. So let me rename this as bottoms. Okay. And let me create a new string for distillate. So let's create a distillate. And I'll tell you what. Well, okay, let's look at the compositions of those. This is if I had the others. Then I would get rid of them together with the HCl in the distillate. Okay? So my distillate, so we pure HCl, we have the following composition. 174 chlorine, 203 ethylene, and of course 1623 HCl. So let's do that. So I have ethylene, 203, 174. So we'll go here, composition, molar flows. Select molar flows, and then put for HCl 1622.8. And my memory is bad. Do you remember what was ethylene?
203.
What was it?
203.09.
203.09 was ethylene. And what was
Chlorine.
chlorine?
174.03.
Okay. So, these are the compositions that will be coming out of the distillate. So click OK. Now go to conditions. Specify the pressure, 12 atmospheres. And if I have a total condenser, I'll specify vapor fraction 0. And you can see the temperature will be minus 13 degrees Fahrenheit or minus 25 degrees C. So it didn't change very much. If I had a partial condenser, I'll put 1. And in this case, the temperature goes up to minus 11.8. Not much difference. Minus 12 degrees C instead of minus 25 degrees C that we have. So you raise the temperature to minus 12, allowing a little bit cheaper refrigeration. Yeah.
What are your splits for the, like, do you still have vinyl chloride going up or is it going down now?
Well, think about it. What is the relative volatility? The more volatiles go with the distillate, the less volatiles go bottoms. So the three more volatiles are HCl, chlorine, and ethylene.
Well, I'm asking that because a few days ago when we selected the split, we had vinyl chloride going up.
What do you have going on?
Vinyl chloride, we selected to go up.
Yeah, because that was just the final separation. That's the result of both columns. The second column will have vinyl chloride going up and dichloroethane going down. Okay? I didn't bother to put, I basically did what your text does. I just put a ideal component splitter and we're going to separate the dichloroethane and recycle it. In reality, I will have two distillation columns, and one distillation column will take out the lights, which are HCl, chlorine, and ethylene, and the second column that is coming will separate vinyl chloride from dichloroethane, and the dichloroethane is the B that is being recycled. So this box is really two component splitters in terms of implementation. So the first implementation would have both vinyl chloride and dichloroethane in bottoms, and the three lights distillate, and the second one